right, well, thank you all for coming. And before I begin, let me thank the Friends of the Institute for organizing this lovely event. I had a lot of fun preparing this material. I would like to thank Ellie Petronio as well for the opportunity to show up here. I have to admit that since I got here in September, and since then I've been basking in the quietude of the Institute, and this is really a lovely place to work, and I've been able to be quite productive. But that's not what I'm going to be talking about today. Today, I'll be talking about the interface between math and music. I was asked to give such a talk a few months ago, and I thought to myself, well, math and music, those are both things that I love, so this should be easy. So I started thinking about what it was that I could possibly tell you about at the interface of math and music. Well, it turns out there are quite a few things that are typically explained as being at that interface. The theme that I decided to talk about today is overtones, to put it in short terms, or harmonics, if you'd like. The reason I chose this subject is because, to me at least, harmonics is the most elementary part of music. Elementary not necessarily in the sense that it's easy, but in the sense that it's basic, that it's the elementary building block of our modern understanding of music. I figured this would be a good thing to bring up. So, okay, before I begin, let me just say that in accordance with the rules of mathematical talks, I would encourage all of you to interrupt me if you have any question at any time during the lecture, and I would be happy to answer them as well as I can. Oh, let me mention also before I begin that I wrote my email down here, jauslin@ias.edu. If you have any questions pertaining to the material that I present here, please don't hesitate to write. I'd be glad to respond. Okay, so mathematics and music, vibrating strings and overtones. This title should indicate that what I will be talking about today will be about string instruments. And in particular, I'm going to focus on guitars, which is my instrument of choice. It's the ones that I understand best. And I brought for you two guitars today. Let me just tell you about this one for a little bit. This is a classical guitar. The most relevant piece of information that you could get about a classical guitar is that it has 6 strings. It's already a good start. So let me play these for you. So there's 6 strings. Each of them plays a different note. I have an E, an A, a D, a G, a B, and another E. Okay, so the first question that I would like to address is, why are they playing different notes? What does it mean that they're playing different notes? So from a mathematical perspective, how can I model the fact that these notes are all different? Well, in order to answer that question, I would like to take the point of view of how am I measuring that the notes are different? How are you all measuring that these notes are different? Well, the way that humans tend to measure sound is through our ears. And in fact, so I'm going to pull up here a diagram that I stole from Wikipedia of an ear. The only part that I want to talk about today is this little organ here that's called a tympanic membrane, that is more commonly known as the eardrum. And the function of the eardrum is to vibrate when there's sound around. When there's sound that enters the eardrum vibrates. And the frequency of this oscillation, how fast the eardrum is vibrating, is going to determine the pitch. If the eardrum vibrates faster, then the pitch is higher. If the eardrum vibrates slower, then the pitch is lower. So, if I play this note on the guitar, the low E, your eardrums are going to vibrate at a certain speed that is lower than the speed at which it would vibrate if I were to play a high E. Okay? I can actually quantify this. I can figure out how fast this oscillation is occurring, and it turns out that this low E here is vibrating at approximately 82.5 beats per second. So it's going back and forth approximately 82.5 times per second. That's pretty fast. So let me write this down on, oops, wrong side. Let me write this down on the screen, if my screen will decide to agree with me. Excellent. Okay, 82.5 beats per second. I wrote beats per second as Hz. That stands for hertz. It means the same thing. It's just a shorter way of writing that. And that there is the low E on the guitar, which I wrote here in musical notation. If you happen to know musical notation, this may be helpful. If you don't, it's really no big deal. Okay, so this low E sounds like a low E because it's vibrating at 82.5 beats per second. So I'd like to get a little bit into why it's vibrating at 82.5 beats per second and what are the different parameters that I can tune on my guitar in order to set this. You know, if I'm building a guitar, what do I need to do in order to get this specific note when I play the low string? Well, essentially there are three parameters. The first, which is the one that explains the difference between the pitches of each of these strings, is the weight of the string. The heavier the string, the lower the tone, the lower the pitch. So this low string here is lighter than the top string up here, and therefore vibrates slower and produces a tone that is lower. Okay, so that's the first mechanism. The second mechanism is tension. Each of these strings on this guitar are pulled pretty tight. And if I change the tension, so I can do this by playing around with these tuners here, so let me show you. If I increase the tension on the string, the pitch increases. And if I decrease the tension, it decreases once again. So tension determines the pitch. Let me get this back in tune or else I'm going to get myself into trouble. Okay. Now the third mechanism, which is the one that is going to end up being more relevant for this talk here, is the length of the string. The length of the string determines how fast it vibrates and the pitch that it produces. Now why is this important for a guitar? Well, up until now I showed you that I have 6 strings. I can play 6 notes, but I can't have much fun with 6 notes. I would like to have access to more notes if possible. And the way that I do this is by reducing the length of the string, which can be accomplished by pressing down my finger on the fingerboard here. So you see, let's say I press down my finger here on the 7th fret. If I press down my finger and play the string, the part of the string that's vibrating is the part that's between the bridge and my finger, and no longer the part between the bridge and the head, which makes the string effectively shorter, and by being shorter, the pitch becomes higher. So this is the string without the finger, and with the finger, it's higher. Okay? So, to sum up what I just said, there are essentially 3 mechanisms, at least in first approximation, that determine how strings produce notes, which is the weight of the string, the tension of the string, and the length of the string. And by playing around with these 3 things, I can play pretty much any note that I like to play on the guitar. So, for instance, if I want to play just a little tune, right, I'm just putting my fingers at the right places, and I get the right notes. So, good. Any questions on this so far? Okay, excellent. Now, so what I just explained to you is how the guitar can produce different notes. And so by putting my fingers in the right places, by playing on the right string, by adjusting the tension right, I can play whatever note I want to play. And by playing that note, the string oscillates at a certain frequency. That frequency goes to our eardrums and gets turned into a certain pitch. But now let me put this to you, that if I take another guitar, this is a different guitar, it's an acoustic guitar. The main difference between the acoustic guitar and the classical guitar, which is maybe something that you can see, is that the strings are made of a different material. The strings on the acoustic guitar are made out of steel, whereas the strings on the classical guitar are made of plastic. Okay? And in fact, they sound quite different. So let me play the low E on both guitars. You hear it here. It's the same note, but it sounds different. In fact, the whole guitar sounds different. So let me play just a short tune on the acoustic guitar and the same short tune on the classical guitar to show you that there actually are really 2 different instruments. So. low. Of course. Uh-oh. Yes. Thanks. This one's louder. So I'm going to play the exact same tune on this guitar. So you hear how both guitars sound really different. It's hard to put your finger on what is actually going on, but they're certainly different, right? But the notes are all the same. So if the note is determined by the frequency of the oscillation, how can they sound different? If I play a note on the classical guitar, I'm vibrating at, say, 82.5 beats per second. I play the same note on the other guitar, I'm still vibrating at 82.55 beats per second. So what's different? What's going on? Why are the two sounds different? And this is the question that I'd like to answer today in this section. You would probably not be surprised if I told you that the answer was overtones. So, in order to understand what overtones, yes? Overtones. I'm going to explain what overtones are. Overtones are actually, they're known either as overtones or harmonics. If you've heard of harmonics, then you know what these things are. Sorry. So, what was I saying? Yes, so let me explain to you what overtones are, what harmonics are. To do so, we're going to have to go into a little bit more detail of how strings vibrate, which is something that is rather difficult to do on the guitar because the string is vibrating at 82.5 beats per second, which is quite fast. It's too fast for the human eye to resolve. In fact, the human eye can resolve on a good day 25 frames per second. We're going to have trouble seeing what is going on precisely on this string. So instead of showing you on the guitar, I'm going to show you on a little animation that I prepared of a mathematical model of a vibrating string. Okay. So this is a mathematical model of a vibrating string. The string is attached here on the left and here on the right, and it's allowed to vibrate on the rest of its length. Now, the very first thing that you may notice by looking at this motion here is that this picture that I gave you of the string going back and forth is, well, it's reductive at best. There's some more stuff that's going on here. You see there's a wave going back and forth here that is, certainly could not be characterized as the string going back and forth. Although, the back and forth motion is there. It's in fact, one could argue, a dominant part of this motion here. So what I'm going to do is first I'm going to isolate the back and forth motion and then show you how the motion of the string differs from the back and forth motion. So I'll do this if I can find my mouse. There you are. Okay, so here I isolated the back and forth oscillation. This is just a simple oscillation. Let's assume that this goes at 82.5 beats per second. So this would correspond to a low E, to the sound that I'm playing on the guitar there. And this motion here is called the fundamental mode of the string. Okay, this simple back and forth motion is called the fundamental mode of the string. So, but like I said, there's more stuff going on. It's not just going back and forth. There's this weird thing going on. So what I'm going to do in order to visualize what is going on beyond this oscillation is, from this motion, I'm going to subtract the back and forth motion. I'm going to take this back and forth motion that I know and just subtract it from this motion here. I'll do this now. So what this is how much the string is differing from the back and forth motion, from the fundamental mode. And you see that the motion here, once again, looks almost simple. I mean, there's something a little funky going on. There's a wave going back and forth here. But the dominating motion of this string, let me isolate the dominating motion of the string, would be this motion here, where the string just goes back and forth once again, except that it does it over half of the length of the string. And it does it twice over the string, each time over half the length of the string, instead of one big back and forth motion over the entire length of the string. Right? And now you remember that I told you that the length of the string determines the pitch. So if this motion here is occurring on a shorter length of string, then the pitch will be higher. Okay? And in fact, since this motion occurs on half the length of the string, the frequency, the speed at which this string goes back and forth, is exactly twice the frequency of the fundamental mode. It's twice the frequency of the big oscillation that I showed you earlier. So I can...
Fundamental motion a mathematical term or a musical term?
Fundamental, both. So a lot of these things, the concepts that appear here in harmonic analysis in music are actually used in mathematics in a field called harmonic analysis, which deals with problems that are much more complicated than just strings vibrating. And the words, the vocabulary that was introduced initially for music has been used in advanced mathematical problems. In this way. Yes, so what was I saying? Yes, the frequency. So let me show you the fundamental mode again. So this was the fundamental mode. It's going back and forth approximately once every 3 seconds. And if I look at this other motion here, you can actually check it's going twice as fast as the fundamental mode. Which, let's go back to this number that I wrote here. This 82.5 hertz, that's the fundamental mode, which means that the frequency of this other motion that I show you is twice 82.5 hertz, which is 165 hertz, which happens to also be an E. Wrote it down in musical notation there. And yes, and this second motion here that I isolated for you, that's called the first harmonic, or the first overtone. Okay, so you have the fundamental mode, which is a low E, and the first harmonic, which is a high E. Now what I just showed you is a mathematical model. That's not necessarily, it doesn't necessarily reflect reality. It's something that I wrote down on my computer and showed you on the computer. So let me show you on the guitar, in real life, that these things actually exist. Okay? So what I'm going to do is I'm going to play this low E. Okay? But after having played the low E, I'm going to kill the fundamental mode. So how do I do this? Well, you see in this oscillation here, let me just put the full thing. What I'm going to do is I'm going to put my finger right in the middle of the string here. By putting my finger in the middle of the string, I'm going to stop the string from going through my finger because my finger's there, the string can't go through. And by doing so, I'm going to remove the fundamental mode, but the first harmonic, which is this motion here, if I put my finger at the middle of the string, I'm not actually stopping anything. So the first harmonic will persist while the fundamental mode will die down. So, let me show you this. Let me play that again. You hear how as soon as I put down my finger, the pitch goes up. But it doesn't sound like I'm playing a new note, like if I were to do this. These are two different notes. Here, the motion of the string is still the same. I just took out some of its variables. This note here is part of the previous note. It was already there when I played the low E, as you can hear. So when I play the low E, I'm actually not just playing a low E, I'm also playing this one. Okay? Is that clear? Good. Okay. This is not the end of the story, however, since, as I showed you here, the motion is a little more complicated than just a fundamental mode occurring on each half of this string. There's something else going on. So let me subtract the first harmonic. All right? Now the first harmonic's gone. Now you see things are starting to get a little small. It's starting to be hard to see what's going on. So what I'm going to do is I'm just going to blow this up. I'm going to make it larger so that we can see what's going on. Okay. So we have another motion here. Now once again, there's something going on. There's something going back and forth. But there is a dominating motion, which I can isolate here, which is just the string going back and forth, except that this time, instead of going back and forth twice over the length of the string, it goes back and forth 3 times over the length of the string. Which means that each of these motions is occurring on a third of the length of the string, which means that each of these motions corresponds to a pitch that is higher than the fundamental mode. By how much is it higher? Well, if the fundamental mode is 82.5 hertz, this motion will occur at 3 times 82.5 hertz, which is 247.5 hertz. So let me write this down here. So I have this other motion in the motion of the string as well, which occurs at 3 times 82.5 hertz, which is 247.5. That happens to be a B. Okay? And I can repeat this. I can keep on going. So I cut my string into 2 pieces, got an oscillation going at twice the frequency of the fundamental mode. I can cut my string into 3 pieces, get an oscillation that goes at 3 times the frequency. And I can repeat this for 4 and 5 and 6 and 7 and 8 and so forth. So let me write down just the values of the frequencies up until 5. Sorry, this guy is called the second harmonic, by the way. So this is the fundamental mode, the first harmonic, the second harmonic. Then I have a third harmonic occurring at 330 hertz, which is yet another E. I have a fourth harmonic occurring at 412.5 hertz, which is a G sharp, and so on. I get more and more of these. Now, once again, I showed you this on a mathematical model. Let me show you that these things are actually there. So we heard the fundamental mode. The first harmonic is here. The second harmonic, right, that's a B. The third harmonic gets a little lower. It's a high E. And then the fourth harmonic, that's a high G sharp. You'll notice that as I go along, the volume of the harmonics goes down. This actually makes sense, because when I'm playing this note here, I'm actually hearing all of the harmonics. But I'm playing a single note. I'm not playing a chord. So if the volume of all of the harmonics were constant, then this would sound like a chord. But it doesn't. It sounds like a note. So it makes sense that there is this decay in the volume. Now let me make one more comment about these harmonics. Is if you look at what these notes are, so I got an E, a G sharp, a B, and an E. Now those of you who know a little bit of music theory will recognize that those notes form what's called a major chord. Let me play a major chord for you. So I'm going to play E, G sharp, B, and E. Of course, this one's a little low. So you hear that they actually sound good together. They sound harmonious, right? As opposed to playing, say, another chord, which sounds dissonant. They sound harmonious. This also makes sense, because when I'm playing this note here, I'm actually hearing all of these other notes. Even though they're damped, they're still there. If they didn't sound harmonious, then this note on its own would sound dissonant, right? So the fact that these harmonics happen to be the notes of the major chord is not a coincidence. Okay. Good. All right. So up until now, I discussed this mathematical model of a vibrating string, showed you that the vibrating string is actually composed of a superposition of all of these different harmonics of the fundamental mode and more harmonics, and then gave you an indication on this classical guitar that those harmonics actually exist, that when I pluck the low E, you actually hear the harmonics. Now, you may not be convinced by this. I mean, when I isolate the harmonic, I'm actually doing something. I'm putting my finger down. So who knows what my finger's doing there? Maybe if I can actually hit this note and get it to play. So maybe I'm doing something to the string. So let me go a little further into, evidence that these harmonics actually exist. And what I'm going to do now is I'm going to record myself playing a low E, and I'm going to show you that within the signal, I can see those harmonics. So I'm going to record this guitar for...
You can see them?
Yes, well, I'll show you the plots. I'm going to use this guitar for reasons that I'm not willing to disclose. So this is just a simple microphone. It will just record whatever I do. And, and to convince you that I'm not cheating, I'm going to show you what I do. I'm just going to, when I hit enter here, I'm going to start recording. And there'll be a little bar that tells us how loud the note is. All right. So I just recorded a note there. Let's see what we got. Let's see what we recorded. So let me go over to this guy. Oops. Okay. So this is the signal that we recorded. This here is relative silence. This is when I started to play the note. You see the signal is actually cut off because the note was louder than what the microphone could take. And then I have a dampening of the note, and it goes into a regime here where things start to equilibrate. If any one of you has ever done any video editing or sound processing, these waveforms should be fairly familiar. Let me show you one. That's my voice. I was wondering who was talking to me. So let me show you one interesting thing, I think, is that this is the signal that we recorded. This is actually, it may not be obvious here, this is actually just an oscillation. So let me show you that it is by zooming into this portion here. And you see that the signal is going back and forth in, granted not an extremely simple way, but it is going back and forth. Now, in order to get out of this signal information about the harmonics, I'm going to perform a mathematical operation that is called a Fourier transform, named after French mathematician Joseph Fourier, which will tell me how much power each frequency has. So let me show you what this is, and then discuss it briefly. I just have to choose a sampling window here, which will be 2.5 to 4. Okay. So I'm going to perform the Fourier transform here. Good. And then, where do I have this? I have this somewhere, don't I? Okay. And then I'm going to plot this thing here. So, okay. So what is this? What I plotted here is a plot of the x-axis is the frequency, and the y-axis is the amplitude, is the volume. This is something that we just measured right now. I'd like to emphasize this. Pretty cool. So, what are these different things? Well, this is saying that out of this range of frequencies, the frequencies are how fast the signal is oscillating. Out of this range of frequencies, what was actually there when I played the note were the peaks. The peaks were the only frequencies that were actually excited, that actually occurred when I played the note. And you'll notice that, so I have these discrete peaks here that happen to coincide with these dotted red lines. These dotted red lines I put in by hand. Those correspond to the frequencies of the harmonics. So this dotted red line here occurs down here at 82.5 hertz. This one here at 165 hertz. This one at 247.5, this one at 330, and so forth. So what this is showing is that within the signal, this is information I extracted from the signal. Within the signal, I do see that my signal is actually a superposition of this frequency, that one, and so forth. And you'll notice that there is, in fact, decay. So there is an effect that is kind of specific to guitars, which is that the fundamental mode is actually excited almost as much as the first harmonic, but the second harmonic is lower, the third harmonic is lower, the fourth is lower than the first two, and so forth. At this point, I can get to the conclusion of my talk, which is why the two guitars sound different. Because I performed this same measurement on the classical guitar. I did this at home earlier this week. So this on the left is what we just measured on the acoustic guitar. This on the right is the same plot playing the same note on the classical guitar. You'll notice it's a little less noisy because I recorded this at home. It's less noise at home. But what is the relevant information here? Well, you'll notice that in these two plots, the red lines are at the same places, so the frequencies are not different. The frequencies in this sound here and the frequencies in this sound are pretty much the same. They're 82.5, 165, 247, 330, and so forth. What is different are the relative volumes. So whereas here I have this big peak here, a similarly big peak here, then a lower one here and a lower one here, on the classical guitar I start out with a low peak, then I go to a big peak, then back to a low one, and so forth. So the difference in the sound produced by the classical guitar and the sound produced by the acoustic guitar lies in how the harmonics are mixed in. Not what the harmonics are. The harmonics are all the same for every note, but the mixture of the harmonics, the relative volumes of the different harmonics determine the difference of the sounds. And now this is actually the fundamental reason why different instruments sound different. If I were to play a low E on a piano, I would get the same harmonics, but the tone would be different because the relative volumes would be different. Or if I were to play a low E on a trumpet, I'm not sure I can play a low E on a trumpet. If I were to play a high E on a trumpet and the same high E on the guitar, they would differ because of the mixture of the harmonics, not because of the individual pitches. So I think that takes me to the end of my talk, and I'd like to thank you all for coming and welcome questions.